Um, so today I'll do more on laboratory qubits, superconducting qubits. So I'll ask in a moment if there were any comments or questions from yesterday. So yesterday I gave you the basic setup, starting from your high school knowledge of electricity and discussing energy storage elements, and especially the nonlinear one that's given to us by the physics of superconductivity from the Josephson effect. And today I will begin to put together qubits from those building blocks. And I realized from some questions from yesterday that I should get to a 0 and a 1 soon. So I'll try to get to that relatively soon in today's lecture. And as I said, tomorrow we'll be perhaps concerned more with how you put qubits together to form larger systems and interconnected systems and networks and maybe even computers. So are there in fact any comments or questions or concerns from yesterday? No? Okay, everyone's ready to sit there and take it in. So let's begin. So as I said, I would show you some superconducting qubits, and there are in fact quite a few. I have some sketches here, and I have 8 different sketches. They're not exactly 8 different kinds of superconducting qubits. There are sort of groupings of these sketches. There are a few of these represent subclasses of a category, and some of them are distinguished only by their parameter types. But there are quite a number of different real network topologies. Okay, so the first one is this. So, which we've been talking about, just one isolated Josephson junction basically is a qubit. So this goes, I'll give you names so that it, give you connections to literature or even magazine stories that you read about. So this was always called the Cooper pair box. And I'll derive for you the 0 and 1 of this object in a few minutes. And it should hopefully be clear to you why it's called something that's holding Cooper pairs. But it's a close relative of something that has a different name and really functions quite differently, and which I will also analyze, and which differs only in this, that it was understood, I mentioned this in words yesterday, that if you just have more capacitance, you can add as much as you want. You can go to the electronics store and buy a 3 farad capacitor. Actually, you couldn't. A 3 farad capacitor would be some big thing. Okay, yeah. Okay, 3 microfarad capacitor. Okay, but we don't need any numbers that big. But you can put on anything you want. And if you put on rather more, you get what's called a transmon. And that's been a very popular qubit and a pretty successful qubit, so I'll tell you about that. Now, the other categories, let me keep this around. I'll put it here. So we've got the phase qubit. Where do I have it here? Yeah. So the phase qubit is the same thing, except additionally with an inductor. Actually, there are 2 variants of the phase qubit also. But there's sort of an extreme limit of this, which, and this I won't put too much emphasis on because it represents obsolete approaches, in fact, to how qubits are used, how these superconducting qubits are used, where instead of having an inductor, you have a mysterious thing, sometimes this is the symbol of it, which is a current source. Expressing the fiction that we can, in fact, completely uninvasively somehow pass a supercurrent through this system, pass a current without any voltage drops, but that nevertheless this is really a laboratory instrument. It's somewhat outside in the laboratory, and you dial up a certain number of amperes. But these are both phase qubits. But the current day phase qubit is always done this way. And I will put a little X circle here indicating when magnetic flux is important. In other words, when an explicit applied magnetic field is important for the functioning of the qubit. It is not, and in fact it cannot be, for this structure, except for another variant of it. So maybe I'll even draw another variant. Because in fact, a magnetic flux put here does, in an absolutely definite sense, nothing. Which you can see by using, remember this cut gauge that I talked about. You can put the cut gauge through the capacitor. But the capacitor, which is only sensitive to the time derivative of the relevant variable, this phase variable, is therefore insensitive to any magnetic flux. So the way you say it pictorially is that this wire isn't actually closed. So it's not actually enclosing a magnetic flux. So that if you put one there, it doesn't do anything. You can gauge it away. Here, I'll discuss the examples where that's not true and where the magnetic flux really makes a difference. There is an exception. There's the tunable transmon, which is, again, the same thing, big capacitor, but now this DC squid structure. But that's strictly to make the effective Josephson, the critical current, the effective critical current, or the effective Josephson energy tunable. And tomorrow I think I'll get to, there's a rather popular method of doing a 2-qubit gate that really relies explicitly on being able to, the control element is really an adiabatic changing of this flux. So it's important. Further types, here's one that's rather more complicated. Let's see, I've gotten through these. Okay, there's even another subcategory concerning the Cooper pair box, which represents tunability in a different way, which you would draw and which you really do implement this way. You have a battery and coupled capacitively to this structure. And this is present in the vain attempt to actually control this offset charge. And it sometimes works. Under some circumstances, you do actually control the offset charge. But additionally, and in a sense more importantly, this is a way that you do single qubit gates. That is, if this is a field driven at a certain frequency, corresponding to the transition between the 0 and the 1, which I haven't derived for you yet, then you can get 1-qubit gates. Okay, next one is...
What's the circle with the V? It's a voltage source or it's a voltmeter?
No, sorry, this is a battery. Maybe that's a bad symbol. Let's use that symbol. Well, I could use this symbol in the cases where you're doing a basically DC biasing. I might use this symbol if I'm going to emphasize that it's going to carry an AC field, or it's going to be an applied AC field. Okay, next, the flux qubit. So the flux qubit is traditionally stated this way. It's just a ring with 3 Josephson junctions. And I'll derive for you why 3 actually is useful. Now it comes along with various other things. Each is a capacitor. Each involves a capacitor. And it's useful, at least formally, to take account of the inductance of this structure. Okay, so I just state that one. That's been a very important qubit. I will also state something that you, at least in the old days, you add to it, and I'll explain why, which is that you put, not in contact with it, but you put around it a DC squid. So I hope you were following me as I drew that. So this is yet another ring structure, and there's sort of implied leads, but this was the first way that, and there are even still a few qubits that work this way, where this is the whole package, including the way you measure it. So this outer structure, the last two Josephson junctions in this structure, will be involved not in the dynamics of the qubit itself, but how you read out 0 and 1. There's another variant of which is what is essentially the phase qubit, which is only distinguished in the literature by kind of drawing a rather long inductor, just meaning that the inductance, just by sort of corresponding to this convention, so it's either or here, where you intentionally make an inductor with a large inductance. I may comment on what it means to do that. It actually doesn't mean making the wire longer. It actually means using more Josephson junctions. And then you get what's now called Fluxonium. And that's quite an important qubit presently. And then I think I have a final one. No, well, I have two more cartoons here. Actually, I have a few more, but I won't say them all. One is to take any old qubit, like the Cooper pair box transmon, and then have another structure which you can schematize this way. But this is not a single qubit. This is our cartoon, or this is our start of the sort of optics side of this story. Or this, well, this is just a harmonic oscillator. Or a single mode cavity, or things like that, and it is coupled. So this is a coupling capacitor, so it's coupled in some weak way to a qubit, maybe a Cooper pair box, but it could actually be coupled to any of these others. And this we'll get to maybe tomorrow. I'm not sure yet, but this will actually get us to a, so-called Jaynes-Cummings scenario. So where we have a coupled two-level system coupled to one harmonic degree of freedom. Yes.
Is there magnetic flux somewhere for the phase?
Oh, thanks. Yeah, thanks very much. Yeah, so definitely I stated that I was going to adopt that convention, and then I didn't do it. Yes, that's indeed the flux qubit very essentially uses that flux bias. Actually, the Fluxonium strangely doesn't. That is, that Fluxonium typically is thought of as an instrument that, or a device you will use at zero magnetic flux. Although it's, in a sense, not so important for the Fluxonium as it is for the phase qubit, and the way that it's conceived to act. It's essential. Okay, I'll draw one more just for fun, and I'll actually use it for some further discussion. So here's one of these big inductors. They are actually literally called superinductors in the literature. More inductance, more henries than you would reasonably get from a regular length of wire. Here's another one. There's some Josephson junctions. And you arrange for rather large value capacitors to crisscross here. And then these have themselves capacitances. So I put this up to flatter our chairman today, but this was actually conceived of, I think, by Alexei Kitaev. It's called the 0 pi qubit, and I don't think I'll do full derivations of what it does. I have sort of too big of a menu here anyway, but it too is created merely to embody 1, 0, and 1 two-level system, 1 qubit, with a lot of thinking about avoiding this noise and that noise, and making protected gates possible. So, but it's just another component-wise object, but a more complicated one than any of the existing ones. And it is frankly distinguished by the fact that all of these have been explored extensively in the laboratory, and this one not. This is a theoretical construct at this point. Okay, and this one's not quite a single qubit. This is a single qubit and one harmonic, one extra degree of freedom. So it's a resonator and qubit, and it is in a sense, when we get to saying what's a multi-qubit system, it's this with more, like this harmonic structure with more qubits hung onto it. Okay, so well, not by itself, I guess. This is the first instance of circuit QED, maybe, but it's not really a name of the device. It's a device for realizing quantum electrodynamics in the microwave, sort of in a circuit. Okay, so I feel like I should start doing some deriving. So let's pick one. Actually, I could almost, well, I wouldn't really do it. I mean, I could almost guess the audience to say, which one do you want to hear about first? But that would actually mess up my pedagogical stream. So I would pretend to follow your suggestion, but then I would actually, in 2 minutes, I would get back to what I was going to do. But let's do this one. Well, I don't know. Does someone have okay.
I was thinking you could start with the Kitaev one.
Oh, the Kitaev one. Oh, no way. Forget it, kid. Now that, well, actually, I did. Okay, if you really wanted to know about that one, I gave a lecture in my course on it about a month ago. So you'd see a whole script of a story about that. I'm actually going to use it for some discussion shortly. Actually, maybe I will do it now. Okay, so I'm going to pretend to. I'm going to pretend like I'm totally responsive to my customers here. I'm talking like I still work at IBM, because I'd like to address a question which, well, in a sense, maybe has come up in some of your minds, which is, remember I had discussed the fact that we're going to be discussing Hamiltonians, or I'll be deriving some Hamiltonians in a moment. And there'll be Hamiltonians which are a function of, some flux or phase variables, or a flux or phase variables, and a charge. But who's to say that there's only one canonical variable? In fact, how many canonical variables are there for these various things? I think I will take up that question now. Because for many of these, like this, there's no question. It's just a one-dimensional problem, and I will get a one-dimensional dynamics and a one-dimensional Schrödinger equation to solve. But what's really the rule for how many canonical variables? Because I can put, or I should, in fact, imagine these to be a whole set of canonical variables. And surely when I get to multi-qubit systems, I've got more. So at what point have I got more? And what is, in fact, the count? Now, I'm not going to go deeply into that, but because, one sort of guess, which is very much obviously wrong, is that there's a canonical variable for every energy storage element in the circuit. But that's already wrong here, because there are two energy storage elements, a magnetic and an electric storage element. So the thing is, electric networks have built into them many linear constraints among the variables. Because this is connected in a loop, Kirchhoff's laws tell us that the phase here is the phase here. Phase being, almost the same as voltage. So that's Kirchhoff's voltage law. So these, of course, these were just the same variable, the voltage variable or the flux variable. And so in fact, the rule is that you have to do a little bit of graph theory, or at least that's an important piece of the story, that you need to find, so number of variables. You need to treat the circuit as a graph and identify a spanning tree. In other words, a subgraph that contains all the nodes of the graph and has no loops, and is maximal in that sense. If you added any more branches, you would get a loop. So I'll use this qubit to illustrate that, for example, the tree of this, or a tree, it's not unique, is, I should be using some color, can be taken this way. So it has 3 branches constituting the tree. It's maximal, and if you add back any more of these elements, you complete a loop of the circuit. So it's a maximal spanning tree. And so in fact, although the rules are a little bit more than this, there are in fact 3 independent, so the dimension of this circuit is 3 in that sense. So the number of canonical variables that are needed to discuss this. Now, it turns out that often, and we'll see this happen in a moment, the relevant number of dimensions is actually smaller than that. So, but at least at a start, if you're setting up the dynamics, you go through this, and okay, I have some papers on this from almost 10 years ago to try to get this all straight. And there, as I say, there are more rules than simply counting the number of branches in the tree. Sometimes it's already fewer than that. But there is a set of rules, but it would take a whole lecture basically to develop that. And I would say it's sort of a specialized topic. So, you know, you might ask, why do you bother having a 3-dimensional dynamics just to represent 1 qubit? And, well, okay, maybe we'll get to that. It's clear 1 is sort of enough, and it's enough in all of these other cases. But let's see if I think for a moment. I think it's true for all the other circuits that I've stated by the usual rules. Except this one. This indeed has 2 degrees of freedom. So this one is this one's d of 2, and indeed it's more than a qubit. But all the other ones have a dimensionality of 1, as for its Hamiltonian dynamics. Okay, so now let me again go back. So I responded to you, and we did do a little bit about the 0 pi qubit, but just the very first steps of it. That at least we have the variables. Yeah.
So not counting when the Josephson junction has capacitance, the capacitance isn't an extra.
No, because the junction with its capacitance forms a loop. So they have the same phase variable associated with them. So that's no. And in fact, it's a pure matter of formality whether you consider the Josephson junction as being in the tree or its capacitance. And we've done it both ways. There are various conventions. There's sort of a big gauge group in some sense in this of choosing all these, choosing which tree you use. But it turns out those signs, conventional signs of, which direction is plus for currents and fluxes and so forth, is another sort of gauge group. So there's lots and lots of freedom, actually, in how you set up these Hamiltonians.
So how do you count vertices, say, in the simplest, in the Cooper pair box? How do you count vertices?
A vertex, vertices are, these are 2-terminal electric devices. So the vertices are the termini, the 2 terminuses of those devices. And so, here they are. These are 2 nodes of this graph, and which involve this 2-terminal device and this 2-terminal device. Here there are, I will get to this one in a little while. So here there are 4 nodes of this graph. So, I find with students, I do find they like to redraw these so all these lines come into here. And I say, no, it's sort of a stretch of conductor without nothing on it should all be viewed as 1 node. Okay, so let's go back to the Cooper pair box. And so you think I'm sort of stalling it. I've spent two hours without actually solving anything. But I'll be finished my first solution quantum calculation in 3 minutes, I think, because it's so easy. That because remember what we had, that we said so the Hamiltonian. So now we're going to do Cooper pair box CPB. The Hamiltonian is q squared. I'll get back to the offset charge in a while. Q squared over 2c plus minus, I guess, minus the parameter I called ej cosine phi. That's it. So now that's, okay, now you have to know, but it's sort of obvious that this is p squared over 2m, and this is the potential connected with it. In other words, that up to factors, which I won't sort out at the moment, but surely involves some h bars and e's, you know, basically this is all classical physics up to here, up to and including here. This is still just the classical Hamilton function of this, but we will now elevate q and phi to operator status, and they'll have the usual commutators is proportional to I. So in other words, q is proportional to dd phi. Now, so it's just a matter of solving this, or you know, writing the solutions for this, the Schrödinger equation implied by this. Now, to do that exactly is actually, well, it's a bit of work. It involves Mathieu functions. So, but we won't need any Mathieu functions for our discussion, because we're going to work in two different regimes. In fact, I mean, the distinction between Cooper pair box and transmon is just a distinction of whether a particular dimensionless ratio is big or small for this problem. So let me rewrite this further. I'll go up here.
Why Q is kind of a momentum, some sort of momentum. Why and Q as a conjugate?
Well, okay. Why is it a conjugate variable? This mainly will show my weakness of mechanics. But you recall the Lagrangian. Well, the sign of that, you had a term which was a phi dot squared in the Lagrangian formulation. No, it's not. Remember, okay, now this is where you have to remember your mechanics. You'd flunk your mechanics course if you confused phi dot with q. But q is what is it? It's like the derivative of the Lagrangian with respect to phi dot, if I recall correctly. That's, you know, element of the Legendre transformation, which I didn't want to have to remember precisely enough to lecture about. But anyway, it's these kind of relations that tell you that Q will indeed function as the, I mean, it's this structure that tells you that Q does, up to constants, serve as the conjugate variable to phi.
So small phi is almost proportional to big phi?
Correct. Now that was, remember that probably I can even remember, because there was a phi divided by the flux quantum, and maybe a 2 pi is phi. And I go back and forth between the object with dimensions and the object without dimensions. Okay, so I'll write the Hamiltonian this way, that this involves some d, well, I don't have to use partial derivatives, d squared d phi squared. It has a prefactor with units of energy, so we'll call that EC, the capacitive energy associated with that term, minus the same thing that I just wrote, EJ cos phi. Okay, so that's the Schrödinger equation. Now, with a couple of observations. Well, let's take number one, EJ equals 0. Then the solutions of this are plane waves. I mean the eigenstates, plane wave eigenstates. In other words, the wave function, this is all single particle physics, remember. So the wave function, you know, is proportional to e to the I, well, some wave number times phi. Now, but I've not reminded you of one thing, which is that phi is compact. Remember? So that it's actually this equation on a circle from 0 to 2 pi. So you can view that as saying it's still, the solutions are still this, solutions to the differential equation are this, but this constitutes a boundary condition, a periodic boundary condition, so that this this wave vector is quantized in units. In integer units of 2 pi. Let's see, am I saying that right? Divided by, when phi goes around to 2 pi, no, I'm sorry, it's just integers the way I've written it. So k is an integer. Oh, and the eigenvalues, the eigenenergies are k squared. Sorry, I'm leaving out all constants to make life, like my own life, simpler, frankly. So that's it. And so we could already have a qubit, really bad qubit. So let's sketch that. So the energies are 0, and then 2 at energy 1, because k can be plus or minus 1, and they're both possible. Then 2 at 4, and 2 at 16, and so forth. So, well, where's the qubit? Indeed, the qubit is not really here, but I could maybe pick these out and say that's my qubit. That's maybe not the smartest thing to do. Okay, but we've forgotten yet another thing, which is that I want to bring back the offset charge, or the possibility of applying voltages here, and discuss what that does. Because that's where I have to go back to here and put back Q offset. Now, recall what that, now, what would we be writing in first year quantum physics? Remember, P minus EA over C. So this is, this Q offset in this quantum theory is playing the role of a vector potential, not the real vector potential. So don't confuse it with the vector potential that, that is involved with describing this. Remember, well, I put it here, but I should have erased it again, because I emphasized that, in fact, a real Aharonov-Bohm flux doesn't really strictly does not do anything to this dynamics. But this, and I meant to check, but I didn't, whether the phrase Aharonov-Kasher is actually more appropriate for this particular field. But it's playing the role again of a now fictitious vector potential in this equation. So now we're still compact. We can in fact now this represents a specific gauge, which is a kind of constant gauge. So if I drew this as an actual A vector field, it would just obviously circulate around here. So this is a sort of a vector potential field. So that's the way, or that's the reason why I say this is for this compact variable. This is functioning like an Aharonov-Bohm flux. But I can go to a different gauge again. I can do my delta function gauge, and actually for this problem it doesn't matter so much. But that's a way of emphasizing that this can be viewed as a change of boundary condition at this slice. That will impose a particular discontinuity on that point, or at that point, so that the net result is that the solutions are still of this form, but it just changes the boundary condition. So instead of these k's being integers, they're integers plus, and here's where I would like to say just Q offset, but I'm just thinking what are the constants associated with this statement, and is it worth it? Let me do that. I'll just say plus Q offset, and you'll excuse me for writing nonsense, of course, because this has units of coulombs, and this has units of integers. Oh yeah, of course, it's 2e. I'm sure is what I'm supposed to write here to make it actually correct. And the 2 is Cooper pairs, we always say, or just as a mnemonic, you might say. That, but the whole theory has a 2 in it, which goes all the way back to the fact that we were doing these 4-point correlators. Okay, so the Q offset appears, and it changes the spectrum. So, and changes it in a very easy way, in fact, which is this, that, so I'll write on this axis Q offset divided by 2e. And what I get are parabolas. So I really get, I've still been doing EJ of 0. I'm going to bring back EJ in a moment. So I had temporarily thrown away the Josephson coupling. Now, the most challenging part, I've lectured on this quite a few times, and the most challenging part is actually to draw a nice sequence of parabolas to show what's going on. And this is where one would usually go to view graphs to not make a complete mess of it. But, okay, but I have my little sheet here. That's it, see? You can't see it, okay. So I go over here to 2e, and here everything comes back to itself again. So let's see, it has to go like this, I guess. And the next one is sort of here. I don't know if I need this one or not. There's another one here that's important. Okay. So what this means, so these are the bands of this problem, the energy bands of this problem. But all it means is that this is an external parameter, ideally controllable. I can just move around on this axis by adjusting an external knob, which in this case was in this embodiment is the voltage of this battery. So I can be anywhere I want here. And the qubit that was, well, historically, the qubit that was focused on as the one, the Cooper pair box qubit, was the one here at E, halfway along this spectrum. Because now we're going to, at least initially, at least in this discussion, bring back this, but only in perturbation theory. Question? Well, there are infinitely many of them, but I've chosen enough so that I can point to the parts of the spectrum that I. Oh, wait a minute. Did I? Okay, yeah, I did screw up. Okay, so because what I had labeled before as 1 is actually up here, and the one that's 4 is up. Well, it's up here, in fact. Yep. No, that's not 4. It's somewhere even further up. I'm very bad at drawing this one on the fly. But thank you, at least for that point, that, yeah, I should have at least kept my scales right. I would have had to draw very shallow parabolas to have made that work. Okay, but this point at, well, numerically, I'm not sure what it is, 1/4 or something, is a place where there are 2 energy eigenstates, way separated from the next set. And now, if I do this, if I consider this as a perturbation, the main place where it has an effect initially is at the degeneracies. So it initially just opens degeneracies. So the initial Cooper pair box as conceived was just this. And in fact, the method of control was conceived of as a non-adiabatic changing of this parameter. This is the, well, I'll call it famous in my field, paper of Nakamura in 1999, which built this and had some degree of control here so that they could fleetingly and not very reproducibly apply a voltage pulse that would take them temporarily to here and then back again. And there's a quick change of the eigenvector as you go from here to here, and so the time-dependent evolution is non-adiabatic, so you can actually get some motion on this Bloch sphere. So, okay, finally 0, there, and 1. So that's the Bloch sphere that was the very first superconducting qubit. Yeah.
Presumably, you're breaking the degeneracy by turning on EJ.
Yeah.
What was the tunable parameter that got you to E on the horizontal?
Well, this Q offset. So it's a setup rather like this. That is.
I thought you were doing the original.
No. Well, okay. The original indeed had had a control voltage associated with it. So, right, so it really this one is what I've been talking about. But, well, by whatever means you might say that this Q offset could be varied, but this is indeed the way that it's varied, by applying a voltage, coupling a voltage to the system this way.
Do you really mean that the levels just do that, so there's no crossing or mixing at all, and then so the state that started out at higher energy just comes back up?
Well, not literally, but I mean, if you do the elementary perturbation theory, you find this perturbation doesn't do very much to the states away from degeneracy.
Well, of course, but
Okay.
At the degeneracy, though, so the two states come together. And
Yeah.
The way you drew it is sort of, you said that there's never actually a crossing.
Yeah, that's this or avoided crossing is the phrase we use. Yeah, or that's another language for it. If you're into random matrices, it's level repulsion, eigenvalue repulsion.
Okay, so you're just saying it's a little more generic and it'll tend to go in that way.
Unless you have some extra symmetries which are not present here, you must not have a crossing. That's the principle of this simple mechanics, of the simple quantum mechanics now. Okay, so that was a qubit, and people tried to make it better for a while. Well, actually, the way to make it better is, in fact, to make the capacitance way bigger. But that takes us into a whole different regime. This was viewed as good, and it is sort of good, because it's what's referred to as a sweet spot, if you've been wondering what that phrase means. Now, what that means is that's within a setting where there's a bit of noise. So suppose your voltage source is noisy. Somewhere out here is a resistor. Somewhere in the bad world is some resistor that we haven't shown. But resistors produce electrical noise. And so what they could be doing as a function of time, you try hard to sit right at this sweet spot. And if you had only a resistor and no other problem, you would get some white noise present. This is time. So your control would be jittering back and forth a little bit. That's a classical view of it, but a reasonably good view of it. And here the energy separation between 0 and 1 is extremal. That's minimal. And so to first order, this does not change the splitting of these, and so it doesn't cause dephasing. Whereas if you're sitting out here and you're jittering, then to first order you are changing the 0 to 1 energy splitting, and that causes more dephasing. And these are true. As I stated yesterday, the unfortunate fact is that these things are drifting quite a lot more. So it's sort of a miracle that they, this idea has not been so useful in this case, but has been a useful case further. Yes?
Aren't there actually two parameters for example, starting from the 1? Because there's one for +1, one for -1, and that's why the entry is quadratic in integer plus QF, or should it be absolute of k is integer plus offset?
No, it should not be absolute. The offset is indeed only in one direction. I mean, if I've...
So the parameters are splitting off.
Let me think. Well, if I come back to here, let's see. These were the ones. This is at Q offset of 0. Okay, good. Well, I'm glad you settled that, because I was having a hard time parsing, but.
Cavalier about signs, but it would really make me happier since Q is I del phi to put a minus sign on the first term.
I'm happy to put minus signs anywhere you want. Here? Perfect, great. Okay, great, okay. Yeah, we're not doing Dirac theory where it was. Okay, yeah. Good, okay, so that's it. I mean, that's state of the art, the year 2002 or so was where we were with qubits. And these were pretty crummy qubits, actually. I mean, one could actually get onto this Bloch sphere. Maybe I should have said something. How do we get like a 0? So how do you initialize these qubits? And the answer is you cool them. But that's where the sort of energy scales come in, which I have not stated. But it turns out the energy scales are such that this is, let me say, this scale, which is the scale of, I guess, of EC. So the scale of EC is, I want to state it in the units of Hertz, and that is quite important in a sense. That is, that's the way the experimentalists think about it. And it's in the units of something like 10 to the 10th power Hertz. Now, why is that? Well, okay, it has to do with sort of micron scale capacitors and, or I mean, submicron scale capacitors. I mean, you get it just from usual formulas for geometric capacitance for the sizes that I discussed yesterday. So this is 10 gigahertz. Now, that may not be a familiar unit to everybody, and but here's an important statement that 1 Kelvin is equal to about, if I'm not mistaken, 20 gigahertz. In other words, and KT, this is KT, is H times the frequency. Those are the conversion units in this case. So that's important because these refrigerators go down to about 25 millikelvin. 0.025 Kelvin is the actual working temperature. So it means that if you just put the system here and you wait, then indeed the Gibbs distribution, it has almost all its weight at these temperatures in this state. And so that's how you prepare an initial pure state. And that worked right away. That's not a big problem. But it was what made it necessary to make these quite small, I mean not atomically small, but quite small sort of submicron scale devices. Okay, but let's do more. We're getting to that, yeah. We're going to flip. I mean, this has all been in the regime EC much bigger than EJ, because I just did a perturbation theory in EJ. But it was realized that it was indeed useful to go to the other regime. And
did you drop the EC, I mean, the wave function, or already, or you intentionally ignore the EC in the wave function?
No, I mean the EC, the wave function is the wave function of this operator, of the free particle operator,
Right.
and so it doesn't depend on the numerical value of EC. Its eigenenergy does, but not the form of the wave function, the fact that it's a plane wave. Oh, did I say, by the way,
You should have a EC parameter in the wave function. Maybe like H bar.
well, if you look at the time-dependent wave function, I mean, if you look at the time evolution of the wave function, yes, it will have a time factor, a time phase factor that will involve EC.
I think you would make him happy if in front of K square you put EC.
Yeah.
In front of what?
K square, the line below.
Oh, yeah, yeah, okay, sure. That I don't mind. Yeah, okay, we're gradually restoring units here. Well, I saved one here. I saved one myself, and then now we've saved another one. It's getting really good. Okay. Observe, by the way, that this is a charge operator. You see the symbol N here because if you change the units, you take out dimensional factors. This is just a number of electrons, or a number of pairs of electrons. And so obviously this wave function is an eigenfunction of the number operator. So in fact this integer is, quote, the number of Cooper pairs. So I mean, of course, it's not literally the number of Cooper pairs in the superconductor, which is countless billions or something, but it is the number, it's the relative number of Cooper pairs relative to the sort of uncharged or neutral state. So when you go from one branch to another, you're really changing quite literally by one pair of electrons the number of Cooper pairs, number of electron pairs in this island, this chunk of superconductor, you might say, or relative to the bottom. So that's why it was called a Cooper pair box. That it was really a box holding discrete numbers or moving discrete number of Cooper pairs from one place to another. Yeah.
So what is the scale of this gap? Because you said, just that distance, easy, but you didn't say, or is it easy?
Scale of the gap is the scale of the gap is EJ. So this is of order EJ. So okay, it's something smaller than this. Now, how much smaller? I wrote much greater than, but in fact, 2 times bigger is already enough for this general structure to be true. So it's not much bigger. So it's still measured in these units of gigahertz, basically. So.
The temperature is still smaller than the gap?
I'm sorry, is what smaller than the gap?
The temperature.
Maybe not. Actually, for the kind of manipulations, in fact, you can, this is a little bit of a digression, but even if this gap is very small compared with the temperature, you can do games like pass this parameter straight through here, and if you do it at the right rate, you can end up with a kind of beam splitter, but in momentum space. So this is the Landau-Zehner-Stückelberg phenomenon that people use, not this specific qubit for, but a very related qubit. So there's, if you want it as a qubit, you could devise control schemes such that you only lived at this point, relatively briefly, but then that would spoil the idea of the sweet spot. I'm somewhat going on in my mind because since this didn't really work so well anyway, a lot of these things, we go to a different parameter region anyway, where so indeed we'll explore this exact same Hamiltonian in a different regime. Now I already said Mathieu function, so we can actually get the whole spectrum if we feel like, but in fact, the interesting regime, so the enlarging of this capacitor was meant to take us more or less in the other regime by variable amounts. So I said here Cooper pair box was sort of EC of maybe 2 or 3 EJ. Transmon regime starts about at 1/3. So there's this region around where these are equal, where nobody's found anything very useful to do with it. But okay, let me start completely over again here.
In principle, you can be far enough of that point, right? Because the first day you said that this Q offset was some kind of noise.
Yes.
Like that. So if you don't control it, you can always be.
Oh, you'll be easily far away from that point. Yeah. Okay. The trouble is, you had to have. If you want to know the phase of 0 relative to 1, you would have to know the whole history of that fluctuating offset charge. Now, the metrology has, within this system has improved enormously in the last 10 years. And so now people have returned to the Cooper pair box and said, hey, we can actually measure as the time excursions of Q offset, and we can actually do exactly what you're saying. So there are a few groups that are saying we're going to redo the Cooper pair box, but in a regime where you can actually do basically quantum feedback and know Q offset and correct for it. Could I do what on the what? Oh, because it's the podium, the stupid podium is obscuring things. Is that?
No. It's just that those are useful for that.
Okay. Okay, so maybe I'll leave this. Well, no, okay, no, I thought I'd start over here anyway because I had my sketch here and I was going to refer it to that. But, okay. I've been feeling that this corner is really bad because then half of you are not seeing what I'm writing. Or
Don't worry, it's on the TV.
oh, the TV. Am I on the TV? Oh, wait a minute. Just that board is on the TV. Okay, I have to see. I haven't been noticing this at all. Oh, see, there I am. Okay, I had no idea. Okay, so let's get on to transmons. And I actually have to do the painful job of redrawing these parabolas. Let's review, because it's maybe slightly confusing. You make the capacitor smaller in order to make the capacitive energy less. Does that sound weird? I mean, at some level it does sound weird, but it's because the capacitor is in the denominator. So this EC is something like E squared over C. There's some extra 2's. But by making a big capacitor, you reduce the capacitive energy. You reduce the value of EC. You also maybe work a little bit to make EJ bigger, but that's not the major thing. So we're going to actually go more in the regime EJ over EC greater than 1. They're variable. How big, again, is dependent on details of experiments, sometimes sort of order 10, sometimes even of order 100. There's not much use in going much bigger, because then you have it. As you'll see in a moment, if you go too big, it's just a harmonic oscillator. If you go too small, then all the painful dependence on Q offset comes in. So somewhere in here is a sort of pleasant spot to be. So this is transmon. Did I? Huh? I want to make EC. No, I really want to make EC small so that this ratio is big.
Okay, so you want to change.
Yeah. Really, this completely. It'll be, in principle, the same story, but indeed in a case where this gap is the main point. Because what you find, let me again draw some parabolas. Let's see if I can manage this just this way. Okay, that's maybe, no, I even need a few more. Okay, so what happens as I turn up EJ? Turn down EC is actually more the story, as I said. So you start opening gaps. Actually, already the gaps up at higher energy already tend to be bigger. Just a statement of perturbation theory. But as I go to large EJ, I got strong level repulsion, basically, in these bands. So these bands are therefore forced to start getting very flat. So this gap gets bigger. This lower band then gets, well, I'm not doing anything but almost drawing a straight line. This one has some little vestigial wiggle, some small remnant of the fact that it came from these parabolas. And the next one has maybe a bit more wiggles. Let me at least try to get them right. So wiggling up and down. Okay, so let's stop there. So what's the point of these getting flat? It's best to, in order to understand that, actually I'll leave this up and erase more over here. I should understand what's happening to the wave function in this case. And to do that, I'll really do another sketch of this Schrödinger equation problem. So here I have phase, and I have it's this potential energy U. So it's this cosine function. Now, I don't have to draw very much of it because we know 0 to 2 pi is all I care about. So I can remain strictly in this domain if I want. Now, the idea was that before this was just a perturbation and the wave functions were plane waves, their modulus was constant. But now I'm in a regime where well, as you'll see, the eigenenergy is somewhere here. The first eigenenergy, the one corresponding to this point, is here. So, sort of quote, obviously its wave function looks something like that. So it really becomes confined in the phi coordinate. And then the next one is somewhere here, and it has one node, but it's also still doesn't go very far. It only has some barrier penetration in going into this region. So you can see then why the boundary condition stops mattering very much. Let me sketch the ground state wave function a little bit. Now the Q offset determined what boundary condition I impose, say, at this point. If Q offset is 0, it's just a continuous, it's just periodic, I should say. But for example, if Q offset is E, then it becomes anti-periodic, so that you really go from plus to minus then. But it's all concerns matchings of something that's exponentially small anyway. So that was the great realization, that therefore made the sensitivity to Q offset almost nil. So that if Q offset is fluctuating by large amounts, these bands are basically flat. I've drawn them in the case where this ratio is not too big yet, but a little bit bigger, and they flatten out to a very strong degree. So let me just quote, there's a little calculation which is related to the one that I put as an exercise. It wasn't this exercise, but it's a similar one, only insofar as you can estimate this sensitivity to boundary conditions by some WKB integral of this forbidden part of the, classically forbidden part of the potential. And what you get is that this bandwidth, let me consult my notes so I actually get it right, but I'm going to write you a result of this calculation, which gives you this bandwidth. And it turns out it is of order exponential of minus the square root of 8 EJ over EC. So that's why, if you go to 100 or something, this you can really forget. This is only for the ground, for the lowest branch of this. So it's only for the 0. So this whole branch becomes the 0, and you don't, in a sense, you don't have to distinguish. The wave function is so insensitive to this variable that it's, it doesn't matter where it is. And you get a similar formula with a, I think, smaller factor here, but still exponentially small bandwidth for the 1. So now, well, I'll get probably next time to the fact that this caused things to be a little harder in the sense that what I haven't gotten to is how you measure these qubits. And this one, there's really a charge that you can measure. If you have the right kind of electrometer nearby, you can measure the qubit. Here you've lost that sensitivity, so you have to have some other scheme for measuring. So that's where this only became a useful qubit when the circuit QED ideas came about, and where you could use kind of optical techniques, in a sense, for measuring this qubit. The reason why you don't go much, much farther in this direction, well, you're collapsing energy scales a little bit, although it's still quite reasonable. For reasonable size metal structures, it's no problem getting this gap to be maybe 4 gigahertz. So it's still in a comfortable range, it turns out. Now, what becomes bad as you go too far in this direction well, if you keep making the capacitor bigger and bigger, then indeed this gap collapses, which is bad. But sort of before that happens, what's happening is that the qubit gets to be too harmonic. Let me explain that by just using this sketch. So let's say I've tuned the parameters so the ground state is here. So clearly the potential, well, I can expand the cosine, and then the problem, if I just stop there, then I would have the simple, harmonic oscillator ladder of states. And you don't want to go too extreme in that direction, because then it will be difficult to use 0 and 1 as a Bloch sphere. If you use usual kind of Rabi flopping techniques for controlling 0, 1, that will actually excite up to the 2 level as well. So you need some degree of anharmonicity. It's actually sketched wrong here in the sense that it's clearer from this picture, because this is smaller. This potential is below a parabola, below a harmonic potential. So in fact, the gaps between the energy levels get smaller as you go up this ladder, not larger. And that also sounds scary, or that was why in the first few years of this work, this would have been considered, crazy, because you have other levels even nearer by. But it was understood that it's just important that they're not at the same frequency, and smaller is okay. So what I'm saying is that E, or let's say omega 1, 2, that I mean, this energy difference, or h bar times omega 1, 2, is a bit less than omega 0, 1. Now, in fact, the amount by which it's less, if you work through the calculation, is, well, this is a negative number, is about negative, I want to say E j, and I believe that's correct. Let me just see. So it's the, it turns out to be the, oh, wait a minute. Making E, no, sorry, it's EC. Yeah, it's the small energy. So that has to be kept under control. I mean, it's important that this not be too small. So that is actually the main thing that limits, that makes the transmon regime somewhere in here. A value of 40 or something is a good number where everything is good. The bands are very, very flat, and this is large enough that the control methods that I'll be discussing are still working reasonably well. They made it up at Yale. It was part of a marketing campaign, basically. The trans part has to do with that it's built out of a transmission line structure, and I'll be a little more clear about that. But, well, I'm slightly cynical about that. I mean, people tried to get their work very prominent by making up names. There are plenty of other things with cute names that we don't mention because they actually weren't good physics. So this one is indeed good physics, and it has some sort of strange name, and PhysRev let it through, or some story like that, or Nature let it go through, or whatever. Okay. Now I feel I'd like to, I'm going to come back to the transmon, because the majority of current day work employs it, but I have various other things that I don't want to forget about, because I did want to actually go through some similar discussion for the flux qubit, just to give you another instance of an interesting dynamics. Really based on very different ideas than this one. Yes?
Yeah, actually, I have a question about that picture.
Okay.
So if you consider Q offset as a fluctuation or noise,
Yeah.
then basically we have a line width, inhomogeneous line width of the ground state.
Yes.
And we want that the line width should be smaller than the separation, the angularnicity, which is
Yeah.
omega 1, 2 minus omega 0. But I think both of them will go over EC, right?
No, because the important thing, maybe I should have emphasized this, this has this exponential. So when you get into this regime, this can be very, very much smaller than EC. That's the point.
What is say, there must be some constant in front of the exponent.
Yeah, okay. So, and that's certainly EJ. So this bandwidth. Okay, so yeah, so even so, though the prefactor constant is larger here than here by this factor of 40, you have this e to the minus 40, more or less, of additional suppression. So that's really the big story, that you get strong insensitivity to charge noise before you get very harmonic. Okay, so let me get to, as I said, I'd like to come back to this because it will, in fact, come into the story of how you scale up, how you make multiple qubit structures, because the transmon has actually been quite useful in making, now there are 3 qubit, 4 qubit, IBM says they'll have 8 and 13 qubits of, sort of functioning little processor based on this qubit. And it did this little innovation, well, with a few other tricks, frankly, made the coherence time of that sort of 4 orders of magnitude longer than the coherence time of this. So it really made a very big difference. So as I say, at least for pedagogical reasons, I want to not completely neglect other qubits. And I thought I'd give you a few insights into how the other ones worked. But I do somewhat use the past tense because, for example, the phase qubit, which I'll now talk about, well, was very strongly advocated by one group in Santa Barbara, but with a following in other places. And they tried very, very hard to have as good a coherence as transmons, and I think they only basically gave up a year or two ago. So there's.
So what affects the coherence?
Well, a lot of it is just the sensitivity to noise. That's a classical phenomenon. The other thing, that's a whole section of my lecture, is what are the further sources of noise besides these sort of semi-classical fluctuations of parameters, of fluxes. Well, okay. Of course, one thing is you should add. Okay, one thing is you should view. There's several levels at which you can do that. I think I probably just erased the thing that I I need to refer to. Yeah. So, for instance, I had Q minus Q offset over 2e, and I have a square here, but I'm leaving a little space. So, suppose I make this a stochastic variable, a classical but stochastic time-dependent variable. So that ensemble averaging over that is enough to do a very thorough destructive job of coherence. So that's one element of it. The other thing is that capacitors really have some resistance associated with them. Now, if I start sketching those, that's fine in electrical theory, and you say, what's the Hamiltonian? But it has no direct, in classical physics, you can't write a Hamilton or a Lagrange function representing the dynamics with that equation of motion, because it's not conservative. So in quantum theory, you would make up a bath. So there would be some kind of bath or environment, and you would write down a system bath theory, and that would lead you to some master equation. And these would be irreversible terms, and that would lead to irreversible terms in those master equations. And so you can in fact build a theory where you say, okay, there's a certain value, a certain number of ohms of resistance, and that leads to a certain strength of coupling to the environment and leads to predictions for T1 lifetimes, for decay lifetimes. Now, these resistors come. These resistors are not very important. well, in this configuration, you would say they have high resistance, giga ohms or something like that. But they are not infinite. And they come from things like substrates. Just recall the capacitors are built from some metal lines that are grown on top of some insulator, and the electric fields of that capacitor go partly into the material, into the support material, and those support materials are insulating crystals, but not perfect. So they have actually some loss associated with them. So there are resistors you can identify. There's also the measurement apparatuses, and I really say plural because there are various ways of measuring these things, introduce connections to the outside world. And so there are resistors somewhere far off that, if you design things right, don't matter so much. But that over time, that took time and experience to understand how to make that so. Okay, so that, in fact, is the few-minute introduction to decoherence. The workers in this field always said, well, there's nothing very fundamental in any of this. They said sort of to the theoretical physicists, they said, don't worry about this. This is really just our problem. Of course, the theorists came along with ideas for how to avoid, make systems that are insensitive to these, say, stochastic terms in the Hamiltonian. So I think the theorists were helpful. But it is true that it's mostly the experimentalists just cleaning up the system that have been the greater contributor to these qubits becoming excellent. So, for example, yeah, I erased all that. I said that, well, no, I'm sorry, let me not get to that, because I'm about to launch into some story about cavities, but I really should hold that off for a while. But the physical design of cavities is actually important in how much resistance you have, and it contributed to another order of magnitude or so of improvement, in fact, of just rethinking how you should make cavities. Okay, but sorry, I did, as I said, I wanted to come back to a few other qubits. So what was I going to do? The phase qubit. I want to do the phase qubit and the flux qubit, but maybe I won't have time, in fact, for all of that. But a phase qubit is something which has an additional inductor. So it was this structure. Now, this was, as I stated, this is again because of the topology of it. It's something with only 1 degree of freedom as a mechanics. That is, there's a phase difference across this Josephson junction. It's the same as the phase difference across all 3 of these elements. So there's only one independent dynamical variable. And in fact, the only thing that this capacitor does is that it adds one more term to the thing that we've already been talking about. So it adds an, I'll call it EL. No, I don't have to call it that. I can just call it what it is, really, which is phi 0 squared over L, and then times phi squared. I believe that's correct. I mean, I'm just trying to get the units right anyway. Phi squared over L. Yeah, I think that's what I want to write. Flux squared over L. So anyway, it's an additional term which is quadratic. Now there are two things that change. With that change, the phase field is non-compact. And in fact, this is this coil spring story, that just by making this added thing, you've changed the topology of the state space. And it is sensitive to a flux, to a real magnetic flux. And it's that flux, not the flux on the other side. As I argued, that one doesn't contribute. But if you thread a magnetic flux into here, it does change things, and so I have to really do what I said before, which is to put in an offset here. I'll call it an offset. This is, in fact, better controllable. So it's proportional to the amount of magnetic flux that's put here. Now, let me explain what that does, or what does this look like, this potential energy. So it's something that has a parabolic envelope. So this is now phi. These are not energy bands. This is just the potential. And it has added to it a cosinusoidal function, something like that. Okay. Now, I've sketched it for 0 applied magnetic flux, where the minimum of the energy of this is here. Then the quantum states would, in fact, be here. What is done to get the system into its the state which is sort of desired for the qubit is to start here and then change the magnetic flux. So change, this is, call it phi external. Change phi external by several phi 0. And I'll explain what that means. So that just changes the origin of this cosine. So as phi is increased, this minimum slides along. I'll slide it along this way. So at some point, so after half a flux quantum, this looks more like this. That is, the minimum has moved to where the maximum was initially, but you move up further. So you move through several several phi naught, which means you you return to this same shape of potentials several times. But if you've initialized the system here, so that's the 0, and you evolve through, let's say, 2 phi naught, then that will adiabatically move to here. And in fact, the concept, which actually goes back to the 1980s, is that the quantum behavior actually up in this higher well, this metastable place, is actually more interesting. The reason why, let me blow up that region. So we're up on a slope. We're on a sloping part of this potential, and we brought the 0 to here. And now there are other metastable quantum levels. Metastable because, of course, these can tunnel through. But we arrange that the WKB integral for that is something quite small. I'm not going to even quote a number for it at the moment, but that's your homework problem, in fact. Yeah?
To add the opposite phase only to the cosine term, but not to the parabolic term.
Right. It's because of my my gauge story. Remember, I can make a gauge where the magnetic flux is here. I can make choose a gauge where the vector potential is only non-zero on this cut, going out to infinity, so that in this gauge it's sort of self-evident that the parabola isn't affected, but it's only affecting the argument of the relevant line integral inside the Josephson junction, just as I said yesterday. There are other gauges where it looks a little different, just in the sense that the origin is moving around with flux instead. But that's, in fact, a gauge-dependent fact. Okay, so the 0 is here, and there's a 1 here. And the parameters are chosen so that this is a pretty shallow metastable well, so it has a few more levels, and then they become too broad to talk about. The line width sort of becomes rather broad. So this was the qubit. Again, a few gigahertz separation can be arranged. This had to do with, I wanted to use this to mention how these were measured. Then I believe I will actually stop. Because measurement was a real struggle, in fact. And the first few ideas for measurement, which were borrowed from older work in this field, they worked, but they were highly non-optimal. So that's been a part of the story, is that the method of measuring has become much better. So
It's much more interesting up there. Why?
oh, well, because it's highly non-harmonic, so that gets rid of this problem of transitions to the next level being also in resonance with external control tones, and it will make it easier to measure, according to the old ideas for how you would measure these. And I wanted to sketch that, because I've sketched this as if it's a little piece of this potential, but originally it was thought of as, let's see if I can...
But what about this chance of tunneling? Can I see it as a disadvantage?
If it's what?
Tunnel through it.
Well, the tunneling is arranged so that if you're in the 0 or the 1, that it's not, that its rate is quite slow compared with the things you want to do with the qubit. I mean, it will eventually decay that way. So that's a real problem with this qubit, that you can make that decay lifetime long, but you can't make it infinite. And in fact, you use the fact that it's not negligibly small to do the following trick. So I mentioned, it's been erased a long time ago, though, that that originally this was thought of as, or was really implemented as some kind of current source. Now, the way that current source was understood was that it was sort of a limit of this parabola. This was supposed to be, a part of the parabolic envelope. But if you put a current source formally into the theory, it just produces a potential which actually falls off to negative infinity. It's that limit, in fact, of this parabolic scenario. So, and this historically was very important. This is a dynamics, or the dynamics in such a potential were often thought about, and the subject of work in the 80s, say, was all about this potential. This was called the washboard potential. Let's see, has anyone ever seen a washboard? Okay. I mean, I'm sure your grandmother used them, or maybe your great-great-grandmother, depending on where you come from. But, you could wash clothes on them. So I always think this is rather antique. In the next generation, no one will know what this thing is. But now the idea of measurement was the following, that you shine some radiation onto the, or when this qubit is to be measured, then this is what was done. That you shine radiation on this, which is about of this frequency, so that 0 doesn't have, there's nothing in resonance for 0. But if you shine it on the 1, it goes up to one of these levels which has a pretty significant line width, meaning that the rate of tunneling through and going into this region is pretty significant. Actually, within a pretty short time, the 1 tunnels. The 1 after this excitation tunnels. So 1 goes to, you may say, 1 star, and then 1 star tunnels out. And then what happens? Well, the wave packet is out here, so to speak, and there's nothing to stop it. So basically, it, rolls down the potential. Now, what does that mean? This is phi. So that means there's a non-zero phi dot in the quantum state at that point. And that, remember, that means there's a voltage. So that, in short, that has made this, that has driven this, this junction normal. I mean, it's now a normal resistor. And it was only metastably prevented from being a resistor by this energy barrier. And so this voltage was a nice macroscopic thing that John Martinez could just measure. And so did indeed measure what the qubit had been. I mean, it's obviously, it's extremely destructive. It's a non-demolition, or it's not non-demolition quite significantly. And it leaves, I mean, non-demolition is not a necessity in quantum information processing. But besides demolishing the state, it also heats it up a lot. So in fact, the qubit would be in this rather bad, very hot state, and you'd have to now cool it down again. And it would take a lot of work, a lot of cooling down and waiting for the qubit to come back. I mean, you'd have to basically recycle it in some way, turn off the external current and let it settle down again, and all the quasi-particles and other stuff. I haven't talked about quasi-particles. And then it would be ready for the next shot of the experiment. So it was very unpromising for any kind of scalable scheme. But still it worked, and it was the way that, for the first few years, moderately good phase qubits were dealt with in exactly this way. But it was understood that it was really better to do it this way. But then you needed a different scheme of measurement, which again is, I have to come to tomorrow, I believe. So in fact, I'm already at my time. So let me stop now. I have to say I've not gotten as far as I thought, but I hope what I have been telling you is informative and interesting, and you learning some theoretical physics by thinking about these things. And so I'll regroup tomorrow, and I do want to get to these questions of how you make transmons scalable and how you implement surface codes and all sorts of glorious things. Okay, thank you very much.